Hello everyone, I hope everyone is having a great day so far when they start watching this video. Today we're going to start talking about balancing equations. This can be a little bit tricky, but I found some good resources to hopefully help us as we continue to keep learning more and more about chemistry and chemical equations. So, some questions. So what are some other kinds of equations you have heard about? So, have you heard the word equation? What comes to mind? When I hear the word equation, what comes to mind for me is a math equation. So a lot of our things about math equations are going to be similar in chemical equations. So let's think about those. So what are some things in math equations? Well, we have variables, equal signs, addition, maybe any kind of operator. Sometimes in math equations we have subtraction, multiplication, but we'll mainly be working with addition. There's also some numbers, and if there's no number in front of a compound, that means it's equal to 1. So, like, for example, if there's no number in front of x, a variable, we assume there's 1x there. And we'll do the same thing for chemistry. So, some objectives by the end of the day is to be able to balance a chemical equation. Pretty easy. That's all we're going to try to figure out by the end of the day. So, please go watch this video. It does a really good job of explaining balancing equations and exactly what it looks like. What I'm going to work through with you guys today is this simulation. So I'm going to actually have you guys play around with this on your own a little bit too. So if you click on this link, it'll send you here to this balancing equations, what's called a simulation. Let me go back to home. We're going to start on introductory. If you guys start to get it figured out and want to play the game, I'll show you how that works too. So I like to use these two different tools. So let's start first with this scale. So the idea here, after watching our video, then we want to get everything equal on either side. So we want the same number of nitrogen, hydrogen on the left side as there is on the right side. So right now, if we were to count this, we have 0 all the way across. So let's give everything a 1 and see what happens. So, for nitrogen, we have 2 nitrogen on the left side and only 1 on the right side. And that's what is shown here. We can see 1 blue circle and 2 blue circles over here. So, to balance out our nitrogen first, we would need to add 1 more. So, now we have 2 nitrogen, but our hydrogen's way off. We have 6 hydrogen over here because we have this 2. And we're going to multiply it by this 3. That's how we count up to 6 hydrogen. If we count the circles, it's 1, 2, 3, 1, 2, 3. So we need to get more on our left side of our equation. We can see we only have 2. If we increase this, now we have 4. If we increase it again, we now have 6. And we get a big smiley face up here. So that's kind of fun. Let's do another one. I want to show you a different tool though. So instead of our balancing scale, we could also do it using this little bar graph is what it looks like to me. So this time we're taking water and we're turning it into hydrogen and oxygen. So let's give everything a 1 just to see where we're at. So right now our hydrogens are balanced on either side, but our oxygens are off. So we only have 1 little red circle, 1 oxygen, but we have 2 little circles over here, so we have 2 oxygen. So if we were to do this, we got to increase our oxygen, to 2. So now our oxygens are happy, but our hydrogens are not. We have more hydrogen. We have 4 hydrogen over here and only 2 hydrogen over here. So if I were to increase this by 2, go from 1 to 2, we would now have 4 hydrogen, 2 oxygen, 2 oxygen. That means everything is balanced and we're happy. I think I like the scale a little bit more, so let's try that one more time for this one. This one is a combustion reaction. We learned about our types of reaction. This is combustion. So we have our carbon over here. Let's give everything 1 just to see where we're at with things. That's how I like to start. So right now, as we're looking at things, our carbon is balanced. We can see that's nice and easy. Our hydrogen, we have more hydrogen on the left side than on the right, and more oxygen on the right than on the left. So we got to balance a few of these things. So let's start with the oxygen. So we have a 2 and a 3. So when I'm looking at this, going to say we need to get this to balance. If we can only go up by whole numbers though, so only up by, or like by doubling it. So if we doubled 2, it would be 4. If we did 2 more, it'd be up to 6. If we doubled 3, it would be to 6. So let's try to get our oxygens on either side to 6. So to do that, I would need to go to 4. Sorry. Actually, never mind. Ignore what I just said. So if I increase this by 1, we're at 4 now. So now all I have to do is increase our oxygen by 1, and we would be balanced. As we can see, as I go from 1 to 2, on our hydrogens start to balance out, and then if I go up on our oxygen, everything is balanced. This link also has a cool little game that you can play where you're practicing balancing your own. So you just plug in what you think it should be and then check your answer. Oh no, I got it wrong. Let's try again. Let's try this one. And it's all happy and I get a smiley face. So I'll have you guys work with that a little bit. I think it's a good tool to kind of break down this a little bit more, keep explaining it more and more in new ways. The whole idea of balancing equations is we will have to get everything on our left equal to everything on our right. And the only thing we can change is our large numbers in front of each compound. So the most important, or I think crucial part of this is learning how to count the number of elements in each compound. So for example, we see C6H12O6 and 6O2 goes to 6 carbons, 6 CO2 I should say, and 6 H2O. So the way we count this is if there's a little number below our element, below our symbol, that means there's 6 of them, or there's that many numbers. So we have 6 carbon right here, we have 12 hydrogen, and we have 6 oxygen in just this compound alone. When we have a little number down below it, that means we have 2 of them. If there's a number in front of it, we have to multiply it by every little number. So what we're saying here in this part is we have 6 times 2, so we would have 12 oxygen right here, 12 O's. Right here, since there's nothing right, there's not a number, we assume it's 1. So if we multiply 6 by 1, that would be 6 carbons. 6 times 2 is 12 oxygens. Same over here, 6 times 2 is 12 hydrogen, 6 times 1 is 6 oxygen. So I counted all these out and wrote them down. On the left we have 6 carbon, on the right we have 6 carbon, 12, 12, 18, and 18. So what that means is this is a balanced equation. We have just as many carbons on the left as on the right, just as many hydrogens on the left as on the right, and same for the oxygens. So let's go through what this would look like when we're going through one of these problems. So the way I like to do them, I think the way that makes the most sense is to count the amount of each element on the left and the right. So I start with putting a 1 in front of everything, like I did on our simulation. I put a 1 in front of everything and see what needs to be changed. So then I find which compound to place a number in front of. So I start looking at, this side has much more or much less oxygens, for example, and I start focusing on there and how can I change that to get it balanced. Once I place a number in front of a compound, I recount just to see how that changed my whole process, changed everything, and then if I need to, I place another number in front and recount, and I continue steps 4 and 5 until everything is balanced. So let's show an example of one. So for this example, we have KOH, which is potassium hydroxide, plus H3PO4, which I think is phosphoric acid. I think that's phosphoric acid. Turns into potassium phosphate and water, I think is how that works. But the names don't matter as much. So our first step, though, is to count the number of elements on each side. So if I was to count the number on the left side, there would be 1 K in this compound, 1 oxygen, and 1 hydrogen. Now I have a hydrogen and an oxygen in this compound and in this compound. since there's an addition sign right here, I would add them together. So this says H3, that means there's three hydrogens right here, and there's one here to get 4 hydrogens. So 4 hydrogens in total on the left side, 1 K, 1 P, or 1 potassium, 1 phosphate, and then we have 4 oxygen here, and this one over here makes 5. And we can count the right side the same way, but we'd have 3 Ks right here, 1 P, 4 oxygen, 2 hydrogen here, and 1 oxygen. So I just wrote those out. I find it helpful just to write them out, and then I can look at them this way and say, okay, my oxygens are balanced, my phosphorus are balanced, or my O's and my P's are balanced, but I see this K is unbalanced, and I see this hydrogen is unbalanced. So step 2 is, where should we put a number? So I would like to start by balancing our K's. So, this is kind of just what I was talking to. So if we have 3 K's on this side, but only 1 K on this side, and we can only put a large number in front of each compound, let's try putting a 3 in front of this 3KOH and see how that changes our numbers. So let's recount. So now I put a 3. It's the same equation. These all are the same, but I put a 3 here. So let's count. Our left side now has 3 K's, 3 plus 3 H's, 3 plus 4 O's, and 1 P. And our right side stayed exactly the same. So all these numbers I didn't change. And now we see that we have a hydrogen and an oxygen unbalanced. So it's like, oh boy, I feel like I almost went the wrong way. But on the bright side, I have a compound that has both hydrogen and oxygen on the right side. So let's look at our next step of determining where to place our next number. So if we were to put a 2 in front of our water, our H2O right here, it would be 2 times 2 hydrogen, so 4 hydrogen, and then 2 times 1 oxygen. So we would get to recounting it. So I just recounted those after putting a 2 there, and then our balanced equation would look like this. So again, if we looked at it this way, we still have our 3 Ks, we have our 1 P, we have 4 plus 4 oxygen, and then, 4 plus 2 oxygen, 2 times 1 is 6, and then we have for our hydrogen 4 and 4, 1, 2, 3, 4. So we would have a balanced equation. I apologize, I am just realizing that my numbers are off here. So what I have here, let me show you guys what I did wrong. So I said we should multiply our hydrogen by 2, or our water by 2, but it really should be 3, so that we need 6 hydrogen and we need 7 oxygen. I put a 2 when it should have said 3. I really apologize for that confusion. I just started counting it in my head and realized that I had it wrong. So this should be, let's put a 3 in front of water and then recount. So now if we look at it, it's, sorry about that, it is 3 times 2 is 6, so we have our 6 hydrogen, we have 3 times 1 plus 4 to get to our 7, and we're all balanced. I apologize for that confusion. That's why we always recount and double check. So our real balance equation is a 3 and a 3 here. So I want you guys to try this one on your own. It's a little bit simpler. We have MgO2 goes to MgO. So please pause the video for a second and try on your own. But I'm going to count either side of them. I notice that we have a magnesium on either side, and then 2 oxygen on this side, and only 1 on this side. So I put a 2 in front of MgO and recounted. And then I had to place a 2 in front of the Mg and recount to get all the way to our balance equation of 2Mg plus O2 goes to 2MgO. So that was a little quick. I was hoping you guys were understanding it a little bit quicker on this last example, but if you guys have any questions, we'll do some more practice, but please let me know if you have any questions. Thank you.